So I will talk about the crystal basis for generalized Kac-Moody algebras. So I will start with abstract crystals and highest weight crystals P infinity and P lambda, and we'll talk about the geometric construction. And this is joint work with Masaki Kashiwara and Olivier Schiffman. So let us recall the definition of monster, the largest sporadic simple group, which was discovered by Fisher and Grice. And its order is close to 10 to the 54. And if we use Buddhist numerology, then it's between like 10 to the 52 and 10 to the 56. So somewhere like it's more than the number of sands in the river and something like that. So Fisher and Livingston and Thorne computed the character table. And so character table is just this. I mean, you compute the two each conjugate class, you compute the trace. And trivial character is, of course, dimension of the representation. But for the monster, the first non-trivial representation has dimension 1968A3, which is important number. Again, the second non-trivial representation has this dimension. And as you know, McCain noticed that 1 plus this number is this, which is quite striking. And actually, it is really striking because there is a mistake, right? So this is a mistake. You just add 1, and if you add these 3 numbers, then we will get this number. And the reason why this addition is striking is that they are the coefficient of the modular function J. So motivated by this observation, Conway and Norton made the following conjecture. So there must be Z-grade representation, which is called the V natural of the monster, whose grade dimension should be modular function J. And moreover, if we compute the graded traces, which is called the McKay-Thompson series, then that must be the output module for some discrete genus zero subgroups of PSL to R. So in particular, when G is identity, we get the modular function. And so for each G, actually for each conjugate class, there is some discrete genus zero subgroup, and its function fields has one generator, which is this McKay-Thompson series. That's moonshine conjecture. And to prove the moonshine conjecture, Frankel, Lipovsky, and Morman constructed vertex operator algebra, using vertex operator algebra, and constructed the moonshine module V natural, and verified the moonshine conjecture for some conjugate classes of M, monster. And in 1992, Boltzers completed the proof of the moonshine conjecture. And his idea was to use monster Lie algebra, which is Z by Z graded Lie algebra, and using the Euler-Poincare principle of Lie algebra homology. So, and show that both McKay-Thompson series and the suggested output modules satisfy the same replication formula, and the first few coefficients are the same, so they must be the output modules. That was his idea of proof. So here, point is that the monster Lie algebra is a generalized Kac-Moody algebra. So, what is generalized Kac-Moody algebra? Well, we consider so-called Boltzers-Cartan datum, but for simplicity, and in this talk, we will consider only symmetric, even integral Boltzers-Cartan matrices. So diagonal entries are even numbers, which are less than 2, less than or equal to 2, and off diagonals are symmetric and non-positive integers. And we denote by R super RE, so the so-called real indices corresponding to diagonal entries 2, and then if diagonal entries are less than or equal to 2, then we call them imaginary indices. And for this Boltzers-Cartan matrix, we can associate a Borchers-Cartan datum. So A is a Borchers-Cartan matrix, and P is a free abelian group, and pi is a linearly independent subset of P, and pi check is just this basis, some of the basis of this. No, some of basis of this. Well, some part of basis of this, which are called simple chorus, and they must satisfy these three relations. So hi and alpha j gives entries of Borchers-Cartan matrix, and pi must be linearly independent, and there is to be some fundamental weight which is given satisfied, which is given by Kronecker deltas. Now, to each Borchers-Cartan datum, we can define the quantum version of generalized Kac-Moody algebras. So it's quantum deformation of universal enveloping algebra of Kac-Moody, generalized Kac-Moody algebras. And these are actually given similar to Kac-Moody algebras. But the quantum set relations hold only for real indices. And for imaginary indices, we don't have any relations unless Aij is 0. In this case, Ei, Ej, Ei, they commute, and same is true of Fi's. Then, well, for this, one can define the notion of integral modules in category O. And we can develop the crystal-based theory following the framework given by Kashiwara in 1991. But motivated by this, we can define the notion of abstract crystals as follows. Here, Monica wanted to explain this before, and actually everything else is the same, but except for imaginary indices, epsilon I is not changed, phi I is changed by aii. Actually, this is because we would like to keep this equation so that we can define the tensor product rule more uniform way and in a clear way. And so that true for here too. Epsilon I is not changed by fi tilde, but phi I is changed by aii. And this is the same convention that we use for Kac-Moody case. Then, a crystal morphism is a map which preserves weight, epsilon I and phi i's, and which commutes with fi tildes whenever fi tilde is not 0. Okay? And crystal morphism is strict if it actually commutes with all Kashiwara operators, and it is called an embedding if the underlying map is injective. Then, the best known example of abstract crystal is so-called highest weight crystal. So let V lambda be the highest weight, irreducible highest weight module. Then, using the so-called I-string decomposition of elements, we can define raising and lowering operators, which are called Kashiwara operators. And from here, if we consider this, a knot span of elements obtained by applying Kashiwara operators on highest weight vectors, and consider the non-zero vectors modulo Q is 0, then this B of lambda is an abstract crystal. And on this B lambda, the combinatorial structure of V of lambda are all encoded. So this B of lambda becomes an abstract crystal. So this is best known example for abstract crystal. And here I would like to emphasize, well, actually, I hope you pay attention to this. Here, for real indices, epsilon I is the number of arrows coming into that vertex. But for imaginary indices, we just define it to be 0. And for the number of arrows coming into the vertex, we have different name. Sometimes we need it. All right. And another example is the crystal basis of UQ minus. And we can define Kashiwara operators in a similar manner. Then this B infinity is the crystal graph of UQ minus G. And we can define an abstract crystal structure on B infinity 2 as usual. Now, next example is so-called elementary crystal. So for each I, let B sub I be the, actually it corresponds to non-negative elements, non-positive integers. So its element is denoted by Bi minus n, negative n, and weights are given by n times, negative n times alpha I, but Ei and Fi tilde, they raise and subtract indices, otherwise it's 0. So if we define this way, then B sub I becomes a crystal, which is called an elementary crystal. So now the elementary crystal plays an important role in realizing the crystals B infinity. And so finally, well, therefore it also plays an important role in realizing crystal B of lambda. And for abstract crystals, we can define the tensor product as usual. So for using phi I and epsilon I, we can define Cauchy operators. And for real indices, the Ei tilde is given in the same way as we do for Kac-Moody case. But for imaginary indices, here is the difference. So this is same for Kac-Moody case. And here, if epsilon I b prime is between these two numbers, I mean, then it's 0. Okay? Because Ei tilde and Fi tilde are supposed to be almost inverses to each other. So that's why we define this way. Then tensor product becomes naturally an abstract crystal. Then for generalized Kac-Moody algebras, in the joint work with the Kashiwara and Jung and Shin, where there is natural injective map from B of lambda to B of infinity, which satisfies these properties. It is an embedding in some sense. So I think this is part of the goal that Peter Tingley wants to understand. We would like to understand this embedding. Oops. Yes. And there is crystal embedding theorem. So even for the generalized Kac-Moody algebras, this is known for Kac-Moody case, but for generalized Kac-Moody algebras, there is unique strict embedding from B infinity to B infinity tensor B sub I, elementary crystal. So we can repeat this embedding many times, sufficiently many times, and we can realize B infinity as a sequence of elements in infinite tensor product of elements in B sub I. But the problem is how to characterize the image in this embedding, because this is not an isomorphism, it's only an embedding. Now, using that embedding, one can give characterization of B infinity or recognition theorem for the crystal B of infinity. So if B is a crystal satisfying the following three conditions, so weights are in negative root lattice, there is an element of weight 0, and for any element which is not equal to this element, then one can move upward. That means eventually this graph should be connected to B naught. And for all I, we have strict embedding. Then if the crystal B satisfies these four conditions, then that crystal must be isomorphic to B infinity. That's a recognition theorem for B infinity. And secondly, for B of lambda, we consider a crystal consisting of single elements T of lambda and C. T of lambda has weight lambda, C has weight 0, and Ei tilde is all 0, but the epsilon I and phi I are defined differently. Then this B of lambda is embedded into this crystal, and the isomorphic to the connected component containing this highest element. So the B of lambda can be characterized as a connected component in this crystal. So this is another recognition theorem for B of lambda. And when you construct abstract crystal and we think this is candidate for B of infinity over B of lambda, then we can use these two theorems to recognize them as B infinity or B of lambda. Now, the problem is how to construct or how to realize the crystals B of infinity and B of lambda. And today, I will talk about the geometric construction. So, let I be the set of vertices and H be the set of arrows, and IH be a quiver with orientation omega. So H is a disjoint union of omega and omega bar. Here bar means if you have H, then bar means you just reverse the arrow. So we also define epsilon, whose value is 1 if H belongs to the orientation and -1 if H does not belong to the orientation. And we will use this notation: outgoing vertices by out H and incoming vertex by J in H. For this quiver, for a quiver, we will denote by Cij the number of arrows in H from I to H, and we define Aij to be 2 minus Cii if I is J and negative C of Ij. So here point is that in this quiver we allow loops. We allow loops at each vertex so that if Cii is 0, then we get the usual real indices, and if Cii is positive, then we get imaginary indices. So in this case, for generalized Kac-Moody algebra, we allow loops. Then the matrix defined by this condition is a symmetric, even, integral Borges-Cartan matrix. Okay. And well, for the representation of quiver, we define the dimension vector as an element in positive root lattice whose coefficient is dimension of V sub i's. And we can define the inner product between, well, bilinear form between these dimension vectors in a usual way. And also we consider the algebraic group acting on V. And we define the variety x of alpha to be the representation of quiver, harm V out H to V in H. And also we can define the symplectic form using the traces in the usual way for Kac-Moody case, which is must be familiar to many people here. And we also consider the moment map in a usual way as in the Kac-Moody case. But again, point is that we allow loops. Okay? So to define an analog of Lustig's quiver varieties, we need to define the following. So first, recall that Lustig's variety is the set of nilpotent elements which are maps to 0 by moment map. That's Lustig's quiver variety. In this case, nilpotence condition is encoded here, so we have I-grade complete flag such that XH is nilpotent if H does not belong to the loop. Does it belong to the, it's just strange. First, let me go back here. XH can be just upper triangular for the loops, not in the orientation. And for other elements, XH should be nilpotent. Okay. It's difficult to say in English. For those arrows which do not belong to the bar orientation loops. All right. And second, well, this is the pre-image of, these are linear maps which are mapped to 0 by moment map. And finally, for these linear maps, we ask them to be regular semi-simple. Okay. So these two conditions are special for the quivers with loops. Then one can prove that this is a Lagrangian variety, and we can define epsilon I x to be the codimension of this characteristic subspace. So as if you, in terms of picture, then we consider the arrows from J to I coming to I, and J is different from I. So consider the image of this. So, and in Kac-Moody case, we only consider this space. But in generalized Kac-Moody case, we consider the algebra generated by these loops and consider the image. Then epsilon I x is the codimension of this space inside Vi. Okay. Then we can define stratification, and we can choose an identification of V sub I with the Vi dual space, and define stars for X using the transpose and reverse of the arrows. Then we can define epsilon I star X to be the epsilon I X star as follows. Then it is the same as this one. So star was used to check in Vajrayan's talk, but this is for generalized Kac-Moody case. And we consider set of irreducible components of this analog Lustig's quiver varieties. Then for choosing for a generic point, we can define epsilon I and epsilon I star, and we take these numbers to be the epsilon I of lambda and epsilon I star of lambda, where lambda is an irreducible component of this analog of Lustig's quiver variety. Okay? Now, so we can prove this lemma easily. So in particular, if epsilon I is 0 for all I, then alpha must be trivial. So we have a point. And similarly for epsilon I star, then this lemma tells us that at least we have one vector B naught in the crystal B. So for here, we define this space of points. I mean, it is actually the set of embeddings and projections. This is the main point, which commits with embeddings and embedding and quotient projection map here. So when we choose this to be L times alpha I, then we can have projections from X alpha cross X L alpha I to X, from here to X alpha cross X L alpha I, and from here to X alpha plus L alpha I. And let us consider the inverse image of Lustig's quiver varieties inside here. Okay? Then this projection map is restricted to these varieties, but P1 is not surjective in general. So we take regular semi-simple things in the sense that for each X prime and X double prime, these two maps have disjoint eigenvalues, I mean spectra, okay? Distinct eigenvalues. Then we can have this P1 is surjective. Now, using these three maps, we can define these varieties, but the point is that, so the P2 is a principal bundle, and P1 is an affine vibration. The composition of natural production affine vibration. So the fibers are smooth and connected varieties. That's the point. So by this theorem, one can prove that the irresistible components with the epsilonized L and irresistible components with the epsilonized 0 are in one-to-one correspondence with each other. Therefore, we denote this one-to-one correspondence by EI tilde L. So from an irresistible component with the epsilonized L, the corresponding component with the epsilonized 0 is denoted by epsilon I tilde to the L of lambda. Okay? So from alpha, you subtract L alpha I, but by doing it, epsilon I is reduced by L. Then, using this one-to-one correspondence, we can define Cauchy operators from B to the, we need this. But as follows. So from here, lambda, we go up as much as possible, up to epsilon I much, and we go down by L minus 1 by the inverse map. Okay? Because there is one-to-one correspondence, we can do that. And if epsilon I lambda is 0, then we take epsilon I tilde to be 0. And if epsilon I lambda is L, then we go up as much as possible, and then come down by L plus 1 times. Okay? Then the other maps are defined naturally. So weight of this irreducible component should be negative alpha, and epsilon I prime is the same as epsilon I lambda when I is a real index, but we take epsilon I prime is 0 when I is an imaginary index, and 5 lambda is defined to be this by this equation. Then the set B with the weight epsilon I tilde, Fi tilde, and epsilon I prime and phi I, they form an abstract crystal for generalized Kac-Moody algebras. Okay? Now, how do we realize them as a known crystal? So here, we prove that we can define a map from B to B tensor B sub I as follows. First, take the epsilon I star, which is epsilon I over lambda star, so we'll transpose. Then we apply epsilon I EI tilde star C times, and we come down by C here. Then this map is a strict crystal embedding. So let me go back. So this theorem and this embedding theorem are crucial part of the realization. So by this, what we can do is we can identify the set of irreducible components of Lustig quiver varieties with the crystal B infinity for negative part of generalized Kac-Moody algebras, quantum generalized Kac-Moody algebras. And as I said, the idea is that B satisfies the characterizing, recognizing properties of B infinity, which I showed you before. Okay. Now, how about the highest weight crystal B of lambda? So here, we will try to cut some part of B of infinity. And the idea for Kac-Moody case is we will use stability condition, and we will cut out some part of the crystal B of infinity. So here, for each dominant integral weight, we consider a subspace which corresponds to highest weight. Recall that we consider the subspace V which corresponds to root alpha, but in this case we consider subspace which corresponds to highest weight lambda, in the sense that weight of lambda is defined to be the lambda, and the coefficient is given by dimension of these subspaces. Okay? And define x of alpha was a Ham space. I think we should go back. Maybe I cannot go back. I don't want to go back too much. So x alpha is a Ham space among v's. V stands for the root alpha. And this is the graded homomorphism between V alpha, V and W, and graded homomorphism from VW to V. So these are graded homomorphism. So it's just a homomorphism between Vi to Wi. And you take the direct sum of these homomorphisms, Ham spaces. Then we define the symplectic form as follows. So this is symplectic form on X alpha, and we add this term, take care of these elements. Okay. And then it is a symplectic form on this variety. And we define the moment map as follows. So this is the moment map on X alpha, and we add these two because we added graded spaces. And this same as Kac-Moody case so far. And then moment map is a map here. And we can define stability condition similar to the Kac-Moody cases. So for an element, a graded subspace is called X stable if it is stable under this map. And a stable point in this variety, where a point is called stable if there is no non-zero graded X stable subspace, which are annihilated by all Ti's. So let's go back to here again. So here we denote by X, Ts, the general element here. Then stable condition is that if there is no non-zero graded subspace, stable subspace, which is mapped onto zero by all Ti's. So if it belongs to the kernel, then it should be zero. That's the stability condition. Then we define Nakajima's quiver varieties to be so inverse image of moment map condition. So this must be mapped on zero by moment map and the stable, but also the marked out by the action of GL. But this is rather too big for us. So we have this variety. So here, this was the Lustig quiver varieties, and then consider graded homomorphism from V to W only, and we take the stable points here, and marked out by GL alpha action again. Okay. So, and we will deal with this variety, and then one can show that this variety is a Lagrangian subvariety of Nakajima's quiver varieties. And we do the similar thing for n alphas and for the B. When we consider the geometric construction of B infinity, we do the similar things. But here we add T and T prime here because before we only considered X, X prime, X double prime, and Phi prime, Phi double prime. So we consider this exact sequence. This is the same condition for n alpha, but here we need one more condition taking care of T and T prime. Then from here, we also can define natural projections from this variety to this is Lustig's quiver variety, and we have this graded Ham space, and this is Lustig's quiver variety, and this is graded Ham space. Actually, we had map from this, and we added this one. Okay. Then one can show that this is the main point. Well, actually, for point in our variety, epsilon is defined by epsilon I x only. So t does not play much role, any role in defining epsilon I x. So then, as usual, we consider the regular subspace. We can say that, how can I say? Anyway, well, to make these two projections surjective, and we take this subvariety, then the projection map, this projection map restrict down to these projection maps. Okay? Then one can prove that this Q2 is a principal bundle. And then again, if these conditions hold, then the Q1 fiber, yes, the Q1 is smooth, locally trivial, and connected fibers. And connected fiber is important. And if the condition is not satisfied, then this variety is an empty set. So we assume this condition. Then, as in the case of B infinity, we can show that there is a one-to-one correspondence between the irreducible component of this variety satisfying epsilon I is L, and those elements in L alpha satisfying epsilon I prime is 0. Okay? Then we can denote this one-to-one correspondence by EI tilde L, and then the irreducible components in this variety is same as this, and can be, well, since GL alpha acts freely, the irreducible component of this are in one-to-one correspondence with L of alpha. I mean, this variety is obtained by taking quotient by this GL alpha action. So since irreducible component of n lambda alpha can be described this way, and since the irreducible components here are in one-to-one correspondence with the irreducible component here, we have the following map. So from here, irreducible components are in one-to-one correspondence, but from here we get a corresponding irreducible component in n alpha, because irreducible component here is the set of irreducible component in n alpha and this. Okay, so those has non-trivial intersection with the stable points. So from here we get this commutative diagram, and using this we can prove the same things. The following: so if B of lambda is a set of irreducible component of L lambda alpha, then we can define weight epsilon I prime phi I as usual, and we already have EI tilde and FI tilde. We did not already have, we just have, but this is the same as the EI tildes and FI tildes in B infinity case, but except this case, if phi of lambda is 0, then we take phi tilde lambda is 0. Then this becomes an abstract crystal. Now, how do we recognize them to be P of lambda? So, first one can show that this crystal is connected, and we can show that if it satisfies this condition, EI tilde lambda is 0. And these two properties, especially this one, is to prove that actually there is a map from B super lambda to this crystal. Here B is isomorphic to B infinity, so that we have strict embedding of B of lambda into this crystal, which is isomorphic to B infinity tensor T of lambda tensor C. So if this is strict embedding, then connected component must be isomorphic to B of lambda. So the crystal B of lambda must be isomorphic to the highest weight crystal B of lambda. Okay? Now, so again, what we have used is we define the crystal B, script B and script B super lambda, and check the conditions which characterize the crystal B infinity and B super lambda. But what we think right now is that, well, sometime in June, Joel Kac-Moody complained that whenever I talk about crystals, I already talk about the Q deformation and casual operators and I string decomposition, and you can talk about crystals without using Q. That's true. For example, if you consider the Bernstein and constant work on perfect basis, then you can define crystal structure using perfect basis. But again, in that case, the uniqueness, existence of perfect basis come from upper crystal basis, which uses Q. So I don't think we can really avoid using Q. But anyway, even for generalized Kac-Moody algebras, I believe we can develop perfect basis theory in the same token. Then probably one can give alternative proof for this geometric construction too. In particular, for generalized Kac-Moody algebras and Kac-Moody algebras too, if you construct representations on grothendieck groups over Kovalov-Lauda-Rookie algebras, then you can define crystal structure. And then from that crystal structure, you also use this recognition theorem to identify them with B infinity and B over lambda. But even for those cases, if you use perfect basis theory, then you can, since you have basis, action of EI, and which must satisfy the conditions for perfect basis, then you can give alternative proof how to recognizing these crystals with B infinity and B over lambda. Okay, so I think this is the end of my talk, and the final page is just this. Thank you very much for your attention and everything. Thank you.